Good afternoon, all, and our present speaker is Professor Rajesh Sundaresan from IISc. He is currently the Dean of Electrical, Electronics, and Computer Science Division there. And previously, he has held visiting positions at various places, which includes Toulouse Mathematical Institute. And then he was also with Qualcomm, and he visited the division of EECS. Okay, sorry. Currently, he is the Dean of EECS there, and he has visited earlier UIUC and various places. His research interests are in communications, computation, and control of networks, decentralized algorithms, over graphs and networks, network analytics, information geometry, and recently he started working on this decision theory, particularly related to this COVID and these areas where you need to do a lot of this thing. And in fact, a morning while I was watching an interesting video, interesting talk that given by him. Okay, now, right now he is going to speak to us on asymptotics of invariant measures of mean field Markov models.
Thank you. Thank you for the invitation to speak here. I'll dive right in. This is joint work with a former PhD student, Sarath Yashodharan, who's currently at Brown University. Neither is working. So. Okay, so let me begin with the problem formulation. So we have an interacting particle system, and these interacting particle systems have states, which is a countable state space. There are n particles. The state space, we can just take it to be the positive integers, 0, 1, 2, etc. And the state of the nth particle is x subscript n of t. And the superscript n defines the index of the system, which says that there are n particles in the system. Each state, the state of the nth particle is an integer. Now, the particles can transit from one state to another, one integer state to another. There are certain allowed transitions, and these are specified by a directed graph. And so the directed graph has a bunch of edges which are here. Okay, so which are denoted by the allowed transitions are denoted by the edge set E. Okay, so let's look at the states of the n particles of all the capital N particles at some time t, and then capture the empirical measure. The empirical measure is given by this 1 over n summation of the delta measures, the direct deltas at the states where the nth particle is at time t. And that's a probability measure in the state space Z. And these are the transitions which sort of specify the interaction. For each state Z, let's say a particle is in state Z, it can transit to Z prime, and that transition will depend on the empirical measure. So the transition rate, lambda Z, Z prime, will be a function that depends on what the empirical measure of the n particles is. So here is what you see at time t, a Z to Z prime transition occurs at this rate, which is given by the empirical measure. This is mean field interaction, and it's a weak kind of interaction across the particles. Now, if you look at the entire process, the full description of the process, that is a Markov process, and it's a Markov process on the space of n-fold product of the integers. But you can also look at the empirical measure, and that's also a Markov process on M1 of Z, the space of measures which are empirical measures on the state space Z. Now, this is a Markov process, as I have indicated. Its generator is actually quite straightforward to write. So here is, let's say, the current state f of xi. There is a possible transition from xi to another neighbor. The neighbor will involve one particle transits from z to z prime. So z prime sees an increase of 1, z sees a decrease of 1, and in the empirical measure, it's 1 over n increase and 1 over n decrease. But there are a total of n xi of z particles there. So the transition rate for the Z to Z prime empirical Z to Z prime, and therefore the corresponding neighbor xi to, let's say, xi prime. That's given by n xi of Z, lambda Z, Z prime of xi. So that's the generator for this Markov process. Under some conditions, one can actually say that this is a connected graph, and therefore you will be able to move from any state to any other state. And so the generator possesses a unique invariant measure, and I'll call that invariant measure Pn, script Pn. The goal of this particular talk is actually to say something about the large deviation principle for these invariant measures or the stationary distributions of this Markov process, of the empirical measure Markov process. Okay, so here is an example. Where did I come to this particular problem from? So we were modeling interactions in a wireless local area network where there is medium access control. So there are n nodes which are accessing a common wireless medium, and there is interaction across these nodes via the distributed, what is called the medium access control protocol. The state xn of t of a particular node represents the aggressiveness with which this particular node will be transmitting its head of the line packet. And whenever the head of the line packet, for example, is transmitted, let's say a node is in this state, whenever it is transmitted, it will move to a particular state, which is a success state, and that success state is 0 here. But whenever there is a failure to transmit, let's say you're in state 1 and there is a failure to transmit a particular packet, you move to another state, which sort of indicates how many times you have attempted to transmit this packet and have failed. So you attempted once, now you go to the next state. What do these states imply? They imply the rate at which you will transmit if you're in that particular state. And the current wisdom in designing these Wi-Fi protocols are such that you become less aggressive after a collision. And then you move to the most aggressive state if you're successful. If you're successful, then you have an opportunity to continue to be successful because you will be aggressively transmitting. Whenever the two nodes access simultaneously, there would be a collision and you would go to a later state. So that would be the model in a discrete time, and this is a continuous time caricature. And in this continuous time caricature, only one node can transit at any point of time. So here are the transition rates. The continuous time caricature for the wireless LAN system is the following. For you to have a success, this success transition happens, let's say, at some rate Cz, e to the minus some constant with this vector denotes the aggressiveness at each of the states, multiplied by the current empirical measure of the system. So you can see the empirical measure enters into the picture, which sort of defines the field that determines the success transition or a failure transition to the next state. And here is the failure transition from Z to Z plus 1. That also depends on the empirical measure. The C's denote the aggressiveness with which a particular node will be transmitting at each state. So that's an example model, and this is where I came to this particular interacting particle system. The goal of this network is actually there are multiple goals. The goal of this, you can say here, these are interacting freely to be able to transmit their packets in an autonomous fashion where there is no centralized controller. So the goal in Wi-Fi system is have them operate in such a way that packets are successfully transmitted, they come to here, this particular state, and you have as high a throughput as possible. That would be the goal of an engineering design for this particular system. There are aspects of autonomous operation, scalability, adding a new node, etc. And for those things, you have to design a protocol which is sort of like this, where based on the state, they interact in a certain kind of way. So that would be the goal of the engineering goal of this particular system. But our goal is there is a system like this, and we are trying to understand where the system would settle. What would be the operation of this particular system as the number of nodes becomes large, as time becomes.
You tell us the mean field behavior.
Yes, I'm going to describe.
Also, before you go to large deviations, will you do some diffusion around that?
I will show some limit laws, and then I'll go to the large deviations. We'll not do diffusion approximation.
Sorry, why do you call it? This looks like a zero-rate process of this graph that is not really.
So it's a mean field because the jump from here to here for a particular node will depend on how many other nodes what's the distribution of the states of the other nodes. So the rate is governed by the by the interactions that these nodes have, and the empirical measure enters into the picture. So it's mean field because of that. So this transition, for example, Z to 0 depends on the empirical measure, which is the current empirical measure. What's the distribution of states of all the n particles? Any other questions?
Psi is just the empirical measure of all the nodes.
The Xi is the empirical measure at this current time of all the nodes together. And this is something that was highlighted here. Yeah, so the transitions depend on the mean field interaction, and this function is given upfront. Okay, so that's where I come from, but we'll go to the more general one. So the empirical measure process itself is is a path in this space, and it's basically a random element in that particular space. Let's look at a typical element here. So as n becomes large, what do we expect in this system? And that's the mean field limit. So here is a theorem that one can show. Suppose the initial condition, that is, this is the empirical measure at time 0. This initial condition converges as n goes to infinity in some sense, let's say in probability. And assume that these transition rates are Lipschitz continuous. Then if you look at this mu n t process, the mu n t process is a random process across time, and we are looking at a finite horizon. It converges in probability to a limit law, and the limit law is deterministic. So the mu n t converges to something which is deterministic, which satisfies this equation. This equation is called the McKean-Vlasov equation, and it's been known for quite some time. And in the wireless context, in a more general setting, it was proved by Bodanov and others in 2010, where they had some random fields as well. The interaction was governed by additional randomness in the environment as well. So one can therefore look at an n particle system's evolution as something where there is this limit, but the n particle limit is a back off from this infinite particle limit, and there is some randomness around this. And the idea is that the meaning of this particular limit, that it converges in probability, is that you can put a tube around this, and the probability that you'll be outside that tube converges to 0 as n goes to infinity, whatever be the tube size. Okay, so what we are interested in is deviations from this particular limit law. So here is the infinite particle limit. What about another path? What's the probability of being taking that other path which is completely away from this predicted path, which is the typical behavior? So for this, let me quickly give a definition for what the large deviation principle is, and then we'll go to the specifics about the large deviation. Let S be a complete and separable metric space, and you have a sequence of random variables taking values which are taking values in this space xn, and we are looking at roughly what's the probability that xn, which is the nth element in the sequence, what's the probability that it belongs to the set A. The large deviation principle roughly says that you can write this as e to the minus n times the infimum of a certain function in this particular set. So that's roughly what an LDP is. So more formally, we say that this sequence of random variables or measures associated with them satisfy an LDP on the space S with rate function I if there are three conditions. The first one is the lower level sets are all compact. So here is lower level sets associated with the rate function are all compact. So I is the rate function. This is the lower level set, and that's a compact subset of S. There is an LDP lower bound, which is a local condition. So the probability that your random variable is in the neighborhood of some x, you can lower bound it as e to the minus n times ix approximately, this being the precise notion. And there is an LDP upper bound as well, that the probability that your xn is outside this lower level set associated with s is less than or equal to e to the minus ms, and then some correction terms. Okay, so this, if we have our xn sequence satisfying these conditions, we say that it satisfies an LDP. Let's see what the main result that will be our starting point. So here's a theorem from 1995 and also a subsequent version in the Wi-Fi context that was given in 2012. Suppose the nu n converges to nu weakly, that's the initial condition. This is the mu n of 0 that converges to nu in the weak sense. And then you look at the paths associated with the empirical measure starting from this initial condition for the n particle system. That sequence satisfies an LDP in the space, in the D space, with a certain rate function. And the rate function can be written as follows. Because the initial condition converges to nu, your good paths, which will have finite rate function value, will also emerge or start at that particular limit value. So mu naught is equal to mu. And then the mu will be, any other mu naught will essentially lead to an infinite value for the rate function. So the only ones which will have finite value for the rate function are those that start at mu. And then you take any path, mu, that starts with the initial condition nu. That must be absolutely continuous for it to have a finite rate function. And you can also write down the rate function in this particular fashion. It's a variational characterization for this. And if these conditions don't hold, then that particular path will have infinite rate function. So this is a variational characterization for the S, which is the rate function for finite horizon. So just to give you a little bit of an explanation as to what that S of mu is. Here is the limit law. You take another path and call that mu. It must be absolutely continuous. It must start at mu. You can ask what's the probability that this random path might actually not follow this and follow a trajectory around that. The probability is e to the minus n times some function which depends on that path. And that function is this S0t mu. And it depends on the initial condition mu as well. So this is a process level large deviation principle for the finite horizon. And so here is the explanation. So here is the limit law, McCain-Vlasov trajectory. Here is another path. What's the chance that you will be in the neighborhood, your random path for the n system will be in the neighborhood of this? That probability is approximately e to the minus n times this rate function. So that's this is the empirical measure process, yes. You're looking at how it evolves over time. And instead of following this trajectory, which is the limit law trajectory, you're asking what's the chance that it's around here. And it's exponentially small, and this exponentially small, where you can characterize that as well.
U is the initial condition.
Nu is the, so you have your n particles. The n particles have an empirical measure. They could be random. As n becomes large, they are all converging to this point in a weak sense. That empirical measure is converging to this point in a weak sense. The mu here is for the whole process, yes. So this mu is a path. This is an initial condition. Okay. So there's an alternative representation for this. The alternative representation can be written in this particular fashion. I'll not elaborate on this, except that at some point of time, I'll come back to it, at which time I will speak about this a little bit more. The things to keep in mind is you're optimizing this across all possible functions. The initial condition and the final condition sort of matter. So here is the initial condition for the alternate path. Here is the final condition for the alternate path. So those enter into the picture, and also the trajectory will involve some changes. The graph enters into the picture here. So yeah, so this is, so I should have put here FT, all of these FU There's a minor error here. So fu of z prime minus fu of z. I'll come back to this very soon. Sorry. Sorry? The supremum is over the f, yes. All functions which are, they have a derivative in the first one, but measurable with respect to the second. Okay, so as I mentioned, our goal is actually to look at a large deviation principle for the stationary distribution or the invariant measure associated with the mu n Markov process. So what about a large deviation principle for? So that is the state invariant measure, and we want an LDP for that. So let's, for the moment, assume that the McKean-Vlasov equation has a unique globally asymptotically stable equilibrium. That is, I go back to this equation. This is a dynamical system. This dynamical system has a unique equilibrium, and it's globally asymptotically stable. So that's possibly the natural point where things will settle down for this Pn. So the question is for about deviations around that point. So if you look at Pn will converge to the delta function at xi star, and we are looking at deviations from there. What's the chance that you might find the system in a state which is a little different from this, from the xi star? So the way in which this is usually the LDP and the rate function is usually characterized is you look at what is called the Friedland-Wenzel quasi-potential for the system. So the quasi-potential can be written in the following form. You begin your system, let's say at xi star, and then you ask for a deviation. So if you let the system equilibrate, the system is likely to equilibrate where the empirical measure will be near xi star. And then you look for a deviation which is close to xi. And you have all the time in the world. So here is some time t that you're allowed. So this if you fix a particular time, you start a path at xi star and then you end at xi. That will have a deviation. So it's the McKean-Vlasov trajectory is actually for the system to remain always at xi star. And so this is a deviation from that system. So you can ask, what's the cost of this over this finite horizon? So that's S0t for this particular part. The initial condition is xi star, the terminal condition is xi. But then the Friedland-Wenzel quasi-potential is you look at this across all possible times. So you take an infimum of paths starting at xi star, ending at xi across all possible time. And then you write that V of xi as the infimum across all possible paths, across all possible finite times. So one can write the V of xi in this way. And if we do this, then that is a natural candidate for the rate function of the family. And indeed, this is the case for many situations. For example, Friedland and Wenzel proved that this is indeed the rate function for small noise diffusions. We had some work for finite state mean field models where we showed that this was indeed the rate function, but the states were finite in that case. For reaction diffusion equations, Rich Sowers had shown a similar result, but that was a more general state space, but he was looking at reaction diffusion equations. Sarai and Rockner had a similar result for diffusion spaces, as well as this person, Marty Rossian, who had looked at a stochastic wave equation. So for all of these things, this V is indeed the rate function associated with the large deviation principle for the invariant measure. Now, what I want to now show is that there are situations where this particular natural candidate, which is indeed the rate function in all of these examples, is actually not the rate function. So I'll give one example, and this example is that of a system, an n-particle system, which is completely non-interacting. So let's go back and look at a situation where we had the transition rates dependent on the empirical measure. Let's cut the dependence out and make each particle evolve on its own. So here is a state space, and here is the particle that moves back and forth on this without regard to what the states of the other particles are. So a transition from 0 to 1 is lambda f, independent of the empirical measure. And similarly, 1 to 0 or 2 to 0 or z to 0 are all independent of the empirical measure. So the interaction happened through the empirical measure, but now that interaction has now been cut out because it's independent of the empirical measure. So there is no, this is an independent system. So it's completely non-interacting, but one can still think of this as an n-particle system and ask what the empirical measure is and what its limit law is and its large deviation principle and rate functions are. So if you actually go and look at this process, you can ask what would be the invariant measure for this particular particle. It's not interacting with anything else. And it's a straightforward matter to write down via balance equations what the invariant measure is. The invariant measure has this polynomial, has this exponential decay in the state. So it's the probability that the particle will be in Z is some rho to the Z, where rho is given by the forward divided by forward plus backward rates, normalized by a certain constant. So that's what one particle's invariant measure is. But then these particles are non-interacting. So the stationary measure or the invariant measure for all the n particles is the product measure. And if you look at the empirical measure is this particular law where you're looking at n particles and asking what the states of those laws are and taking the empirical measure. If the yns, that is, if the states of the nth particle are IID xi star, this is the invariant measure, then you can ask what the empirical measure is. Sanoff's theorem will say that the empirical measure satisfies a large deviations principle, and the large deviations principle has a rate function which is given by the entropy with respect to the invariant measure. So this comes right out of Sanoff's law. And so what we are aiming for in the interacting particle system is something that Sanoff's theorem gives us in this non-interacting system. Now, here is the key observation. If you actually look at, let's consider these two functions, the identity function from the state space to itself, to the real numbers, and then the theta of z function from the state space to the reals. The theta of z is z log z. Okay. So where z is the particular state. Now, one can show by virtue of this particular exponential decay of the invariant measure for one particle that the relative entropy of a particular measure xi in the state space with respect to the invariant measure is finite if and only if the mean of that measure, so xi I is the expected value of the z associated with that measure. If that is finite, then the relative entropy is finite, and if the relative entropy is finite, that expected value of z for that measure xi is finite. So one can show this, that just pops out of this nature of the xi star. However, if you look at the Friedland-Wenzel quasi-potential associated with this system, one can write down the Friedland-Wenzel quasi-potential. I'll do that in the next slide. That is finite if and only if the z log z associated with this measure is finite. So what one can do to argue that V need not be the rate function, we know that the relative entropy is the rate function in this case, thanks to Sanoff's theorem. So you start with the xi such that the relative entropy is finite, yet V of xi is infinite. For V of xi to be infinite, the z log z z log z mean of this measure must essentially be infinite. So we can find such a measure where find a xi such that the z log z mean is infinite, but the expected value of z associated with this xi is finite. Then the relative entropy is finite, but the V of xi, which is the Friedland-Wenzel quasi-potential, is infinite. So we have a situation where V of xi is infinite, but we know that the rate function is actually relative entropy, and that's finite. In particular, the Friedland-Wenzel quasi-potential is not the rate function. So what is... yes, yeah.
So you had this interacting system, and then you created a non-interacting system. So you create a non-interacting system by assuming that the iterative distribution of their limiting value.
So I'm looking at a non-interacting system. I can view that also as an n-particle system. And I'm looking at the empirical measure of that non-interacting system. If I look at that empirical measure, I can. It's like the state of the nth particle That's an IID system and the empirical measure associated with an IID system. Right? So for which I know exactly what the rate function is thanks to Sanoff's theorem. So I'm just leveraging that result.
Interacting system you described earlier, and now you're using non-interactive independent system.
I am saying that I can think of the non-interacting system as also an interacting system, and I can speak about perhaps for the non-interacting system, writing down the Friedlein-Wenzel quasi-potential, and that one is infinite, whereas the actual rate function is finite. Now, the connection is a little bit stronger than just this, because the way in which you would analyze, at least we would analyze the interacting system, is actually by analyzing the non-interacting system and then transferring the measure from that non-interacting system to an interacting system and through a Girsanov transformation. And that's what one would use to be able to prove these prove the result for an LDP for the interacting system as well. So the connection is a little stronger. This is the non-interacting system is usually the starting point for getting the rate functions for the interacting system. But here you can view the non-interacting system as an n-particle system. I can write down the rate function. The rate function doesn't match the Friedlein-Wenzel quasi-potential, which can also be written for that particular system. A little more specifically, V of xi, that is the Friedlein-Wenzel quasi-potential, is infinite, but the actual rate function is finite, because if one goes to this particular variational characterization of the rate function, one can write this for the non-interacting system as well. This is applicable. If you look at the first, mu t is the end point, mu 0 is the starting point, mu 0 would be xi star, and mu t would be the xi that we would want to end at, which is this place where we want to evaluate the quasi-potential. If you look at the f functions, which are approximations of this theta, and I don't make them dependent on time anymore, they are just constant across time, but they are now indexed by something which approaches this theta, which is the z log z function. By noting that if you look at the z prime, z log z across neighbors, the theta z prime minus theta z, which enters here, is upper bounded by 1 plus log z. And because of the way in which the neighbors jumps to neighbors enter into the jumps enter into the picture, you can jump from z to z prime, and the rates of those jumps are here, and the impact of those is in this particular form. By virtue of the fact that it's at most 1 plus log z plus 1 in my specific graph, one can show that this is this is linear, because e to the log z plus 1 would essentially be z plus 1, and those which have finite z mean will essentially be things which have this quantity to be finite. And so if you look at this rate function, the rate function is xi and approximately theta, this inner product, xi star and approximately theta, this inner product, minus a constant, where this constant comes from the neighbors' rates. And because you don't have too long jumps, this particular is constant. However, xi star is something for which you have a z log z moment which is finite, but xi is something for which the z log z moment is infinite. And so that's the reason why v of xi is actually infinite in this particular example. So you can let these approximations approach the z log z and get that v of xi should be infinite. The way to interpret this, or at least this is my way of interpreting it, what's happening in the system is that your system, to get to xi, it's starting at xi star and it's evolving and perhaps has a deviation that puts it at, let's say, xi. In the stationary regime, you have enough time to be able to cross certain barriers, but in the finite horizon, when your t is finite, you're not able to cross those barriers. So somehow there are barriers that can be crossed in the stationary regime, but these are not crossed in the finite horizon. So what do you do to be able to maybe bridge this gap between the actual rate function and the Friedlein-Wenzel quasi-potential, the situation where the Friedlein-Wenzel quasi-potential is indeed the rate function? So there are these barriers. either you must lift the barrier for the the barrier for the rate function as well in the stationary regime, or you must lower the barrier in the finite horizon. And the result that I will describe is something that lowers the barrier in the, that lifts the barrier for the stationary regime. So the way in which we lift the barrier in the stationary regime is to say that you can't go very far in your dynamics. So here is the jump rate from Z to Z plus 1. In the example that I had, the jump rate from Z to Z plus 1 was lambda f always. Here what I say is that the going forward jump rate actually decays. And when the going forward jump rate decays, you can't get too far away, and the Z log Z moment for the interesting measures will always be finite. So the way that enters into the picture is that the Z to Z plus 1 transition can't happen at too high a rate. In fact, it goes down and it decays as 1 by Z. So that's roughly the statement that is here. And as far as the down jumps are concerned, you jump at a constant rate back to 0. These are the failures and these are the success rates in the wireless LAN example. Okay, so here is a condition for the theorem, for some theorem that I will state very soon. The function Z plus 1, so I multiply lambda Z, Z plus 1 of Xi by Z plus 1. I want, that can depend on the empirical measure, that I want that to be a Lipschitz continuous function. I want Z to 0 jump rate also to be a Lipschitz continuous function. And these are also uniformly Lipschitz across all the possible edges that one has. So that's one condition. And then the second condition that I have is, here is the McKean-Vlasov equation. Let's assume that the McKean-Vlasov equation has a globally asymptotically stable equilibrium Xi star. And if that is the case, here is a theorem that one can show. Under these assumptions, if you look at the invariant measure indexed by n, where n is the number of particles in the system, that satisfies an LDP where indeed the Friedland-Wenzel quasi-potential is the right rate function. So the main difficulty in perhaps proving this particular result here, that we have an LDP for this family of invariant measures, and the rate function is indeed V. The main difficulty is the following. If you take a measure Xi in M1 of Z, that is a measure in this space on integers, probability measure in the space of integers, with V of Xi finite, then you can produce a sequence. The sequence is a perturbation of the Xi, and that perturbation goes down to 0 as n goes to infinity, where this n is the index of that sequence. So it approaches this particular measure where V of Xi is finite. However, this perturbation is such that you can always have Xi m theta, that is the Z log Z measure, to be infinite. And if the Z log Z measure is infinite, Z log Z mean is infinite, then the Friedland-Wenzel quasi-potential for this is actually infinite. So in the neighborhood of Xi, where V of Xi is finite, you have many measures and sequences approaching the Xi, where V of Xi n is always infinite. So you don't have continuity of the V function in this particular space, primarily because this particular space M1 of Z, because Z is countably infinite, is not locally compact. So that's the key issue here. Earlier, we could not restrict attention to the space of measures where the Z log Z mean for those measures is finite. But thanks to the rates decaying, you can essentially restrict attention to only those measures which have the Z log Z mean to be finite. And under these stated conditions, we can restrict attention to this. And the way in which one would essentially prove the LDP in this more general setup is once again to transfer the process level LDP for mu n from the finite horizon to the stationary regime. This is something that was tried by Sowers. And the first step there, the main ingredients in the proof, is actually to show that the V function is finite in this set and infinite outside, for which you'll need an exponential tightness condition. And so one is able to show this exponential tightness condition. The probability that the invariant measure will put mass on a system where the z log z measure exceeds m. That's exponentially small. It's e to the minus n times some constant. Okay, so this is one of the key ingredients which sort of says that you can restrict attention to this particular set, which you couldn't do in the other situation where there was significant movement in the positive direction thanks to positive rates and constant rates all over. Whereas in the new situation, those positive rates of going very far out is somewhat limited. And what that's doing is it's actually raising the barrier for the large time regime, for the stationary regime as well. And then one needs a process level uniform large deviation principle, where the initial conditions, it's a uniform over initial conditions. The initial conditions can come from any compact set. That's another condition that's needed. And then there would be a continuity property that would be established in this particular space. And that continuity property specifically is, suppose I have my xi converge to xi in the space of measures. And in addition, you also have the z log z means converging on the sequence. Then you'll have the Friedland-Wenzel quasi-potential also to converge to the correct limiting value. That's another thing that you use, which sort of is used to bridge gaps to go from the finite horizon to the infinite horizon, to jump small steps. This essentially enables you to make small steps with minimal small steps where xi is close to xi, but only among such xi that you can jump with minimal additional cost, with small additional cost. And then the strong Markov property as well. So I think those would be the ingredients that one would use in the proof. So I'll just summarize now and then raise some open questions. What's the summary? We were looking at the large deviation principle for the invariant measure in countable state space mean field models. I gave one counter example. I can find there are other MM1Q with interaction is also another one where the Friedland-Wenzel quasi-potential is not necessarily the rate function associated with the large deviation principle for the invariant measure associated with the empirical measures. I gave a sufficient condition for this to be the rate function, and that limited sort of the jump rates of going far out. So here are some questions that one could think about. I'll skip the first one. The second one is, I think one needs a generalization of the quasi-potential to apply to these systems. There is a certain way of thinking about the quasi-potential as the cost of finite horizon paths, and then having an infimum across all possible finite horizons. But perhaps there is a generalization of that, and I do not know what the generalization is. That might be the right quasi-potential that one should be looking at. And that would give the rate function for the invariant measure associated with the mu-n process. So what that is a question that we've been thinking about, but we have not made much progress. And so, yeah, if you'd be interested in that, we can discuss that. Thank you. So here's the reference and some acknowledgements.
Any questions?
I think there are two questions.
I'm having a purely theoretical question. How does this relate to the big LDP structure that Feng and Kurtz have developed? I mean, that's a very general structure for general interacting particle systems. It's a complicated theory. You have to work with nonlinear semi-groups and all sorts of stuff. But it's a big picture that is hard to make work. How does this relate to that work? Of course, you have a very specific structure, and that allows you to do all sorts of precise estimates. But is there a general relation that you say, yeah, this sort of also confirms what you would be able to get out of that theory had you had the chance to make all their steps work?
So I think Feng and Kurtz, the general structure that they have, enables us to get up to some distance, and that distance is actually needed. Some of the results that they have on product measures, initial conditions, and then the path. So we use that, for example, to identify what would be the LDP for a terminal condition or for the joint path, joint of the terminal and of the initial and the path. When it comes to infinite horizon, I must say that I don't have a way by which I could apply. So we did think about this, but I do not know of a way by which I can apply their general theory for this specific circumstance. And the specific circumstance here, at least the approach that we seem to be taking, is for the invariant. It's for a system whose we are looking at the invariant measures associated with the system, which is a large time regime. So we don't have good characterizations of the stationary distribution of the invariant measure. So the difficulty lies there. So we have to pass, the strategy has, in all of these methods that we have come across, the strategy has been to go from finite horizon and pass to the limit. We have not been able to see if the Feng and Kurtz machinery is applicable in that circumstance, because the invariant measure description is somewhat indirect. So I think that's my response.
Thank you. I had another question on the specific example where where you do not get the quasi-potential by, but the quasi-potential is not the rate function of the stationary measures. I was thinking of the following setup. Suppose that you first take Donskoy-Varadhan large deviations in large time, and then take a gamma limit in terms of n. That's kind of the interchange of limits that would, if all is nice, would give you the same would give you the same result. But in this example, you do not have Donskoy-Varadhan large deviations, because with low rate you can run off to infinity. So you can somehow run off to infinity and stay there for a long time and then come back. So somehow, coming from that intuition, it feels like the interchange of limit fails. So if you look at the assumptions of your main theorem, are these actually also the ones under which you can prove the Donskoy-Varadhan type large deviations for any n?
So let me go to the, as I think about this, these are the assumptions that I have. So it's about the interchange of limits between large time and n going to infinity. It's the Donskoy-Varadhan theory that we use to be able to, but only from the point of view of in-path space and the transformations and the Gissanov transformation. That gives us the large deviation rate function for finite horizon. But to go to infinity, I don't think we use the theory that they have. And so there is an interchange of limit that one needs to prove, and the interchange of limit we are able to establish in the finite state space system, but not in this. And your question is, are these assumptions exactly the conditions that justify the interchange of limits?
Yeah, so kind of the question is, does the ability to interchange limit in that sense, so first do Freundlich-Wenzel and then t to infinity, or first do Donskoy-Varadhan and then n to infinity, does it exactly correspond to the identification here that under exactly those conditions you actually pick up the rate function v here?
I'll have to think about this a little. Maybe we can discuss it offline. I don't have a ready answer at this time. So we do prove interchange of limits here. But to specifically answer so we take the limit as n goes to infinity, and then subsequently take t going to infinity, and then justify the interchange of limits by arguing uniqueness of the rate function description. So that's the way in which we proceed. Whether it relates to the approach that you have said, maybe we can discuss this offline, because I don't have a clear answer at this moment.
Thank you.
What will be the rate function if it's not weak?
So it is not V in that example, but it's relative entropy. So it is, so in that particular example, it's clearly relative entropy. I think the question that you're asking is related to, it is some relative entropy, but in what sense? And going in this way, let me go back to that V of xi. Going in this way is not the correct way. So here, these are also relative entropies. So each of these is a relative entropy. Each of these is a relative entropy for a finite horizon. But there are issues related to crossing barriers. And those crossing of barriers, to be able to go from xi star to xi, might require, in terms of the amount of time that you need, more than this. For example, here, I'm looking at an n particle system, but a fixed time t. And it's related to the interchange of limit as well. So if I can allow myself a time for exploration, that is from the xi star to xi, here I allow any finite time, but I should allow myself something which is t of n, which depends on n. And chances are it might be more than linear, more than exponential in n. So that's another thing that one can argue here, that for the system to go from here to here, the time that it takes is e to the n times omega of 1. So maybe if I allow myself t of n, where t of n is bigger than exponential, then I might have a means by which there is a v that arises. But I'm speculating here, and it's loose speak. So,
any more questions? Okay, if no more questions, let's thank Rajesh.
Thank you.